Hi, welcome everybody. I'm very glad to be here with you again, presenting this more practical webinar about the applications of the new RiverFlow2D MT model. If you can hear me well, I would really appreciate if you can just drop me a quick note on your chat or question panel, just so I know that the sound is working as it should. So if you can just take a minute to do that. Okay, it looks like you can hear me well, very well. Okay, so let's get started. So today's webinar, it's performing tailings dam break simulations with the new Mud and Tailings RiverFlow2D MT model. So, well, my name is Rheynaldo Garcia. I'm Director of Model Development and Applications at Hydronia and Hydronia Europe. This was prepared with the assistance of Adolfo Correa, who is our representative at Brazil Hydro in Brazil. So I'm very glad to share this with you today. So before you run asking about this MT model, you say, wow, do we have an MT? What about the MD module? So we had, up to now, we had the non-Newtonian hyperconcentrated module for the RiverFlow2D model was called MD because it was mud and debris. So with the course of time and the tremendous applications that we have had of the module in the tailings dam breaks area, we have decided to change the name to MT because we think the mud and tailings flow module is more it's better adapted to what the actual module is being used at. So that's the reason why it's the MT. But in terms of if you are a user of the model and you have that module, you don't have to worry about it. The same functionality that you have in the past is still there. You only have new capabilities. Okay, so I've been informed here that we have reached the maximum number of attendees. We have a limitation, unfortunately, and there will be people that will be left out, unfortunately. But since the webinar is being recorded, you can advise your colleagues if they couldn't enter that they will be able to watch the webinar at a later time. I'm sorry about that. Okay, so we're going to be describing what's the fundamentals of this new module is based upon, and I'll take some time to talk about the equations because I think it's important for the application to understand, what are we really applying and solving in the model. Then I'll go through the more practical part of how to set up the model framework, importing digital elevation model, both for the existing terrain and also for the deposits that you may have on the tailings dam, generating flexible mesh. Then I'll talk about how to set up initial conditions for the tailings deposit in terms of not only the actual elevations of the deposit, but also the properties, the concentrations of each fraction that you may have there. Then another important topic is how to impose inflow boundary conditions, and because when you're dealing with the variable properties model, you need to account for different concentrations also on the inflow boundaries. Then I'll talk about how to enter tailings data, creating maps for concentration and viscosity and yield stress once the model runs, generating animations for depth, concentration, viscosity, and yield stress. These are all new things, concentration, viscosity, and yield stress, since they are varying in time and space. And then I have some closure comments. So before getting going, I want to acknowledge our amazing team that we have the luck to work with at Hydronia. We have the group at the University of Zaragoza led by Pilar Garcia Navarro and some other great colleagues we have there. And then we have at Hydronia and Hydronia Europe also a number of people that collaborate in our effort. And we are really appreciate all that effort. Also at the Inter-American Development Bank, we have an ongoing agreement with the bank by which the model is being applied in almost all of the countries in the region of performance of the bank. I think this support is also one of the reasons that the model is having a great applications base in the South American region, particularly, especially for the bank investments in those countries. Also, I want to thank many of our clients that have been supporting our model and development for so long already. And we have been growing tremendously in the last few months in the user base, particularly in the area of tailings dam applications. And we are also grateful for that. So the RiverFlow2D model with the mud and tailings module, we call that the RiverFlow2D MT model, is a two-dimensional hydraulic hydrological flexible mesh model. And when we say hydraulic and hydrologic, we means that not only the routing of the flood can be represented, but also the rainfall and infiltration processes as you have in a hydrologic model. And in this case, it's a distributed model because each cell, it's independent with respect to the rainfall or infiltration. So you can have infiltration on one cell and that can be different from the rest of the rainfall that occur in the area. The module uses hyper-concentrated non-Newtonian fluids. It solves the equations that I will talk about with the finite volume numerical engine, which is very efficient and very competent in terms of the accuracy that it can achieve by conserving mass almost exactly and also conserving momentum in 2 dimensions. So this is very important because when you're using the model, you can trust that the solution that it's obtaining of the equations is the best that you can expect from a flexible mesh model. The equations and the solution method can provide all the performance that you want for supercritical and subcritical regimes. You can include hydraulic structures such as culvert weirs, bridges, gates, bridge scours, and dam bridges. It is integrated with 2 graphical user interfaces. One is SMS. Presently, we do not include all the capabilities I will talk about in the SMS. We'll get to that in time, but we do include all the capabilities in the QGIS version. which is the one that I will be discussing today. The model can generate hazard maps and also animations of all the variables that it solves for. It's high performance because it can solve the equations in the GPU, graphic processing unit hardware, and also in cloud computing. And our test indicates that for hydrodynamic computations, we can expect speed-ups of up to 700 times faster than the non-parallelized version of the model. We provide 3 different optional modules that are the water quality, the urban drainage that is integrated with EPA SWIM. We recently released the GPU version for the UD urban drainage module, the suspended at mid-load erosion deposition ST module, and last but not least, the MT Mud and we'll still call it Mud on Debris Flows and Tailings Dam module. So it's the new module I'll discussing today. Now we had a presentation, webinar a month ago or so, where I described briefly, the capabilities, but today we are going to get more into the practical aspects and more fundamental aspects of the model. Well, first, the model uses flexible mesh. Maybe many of you are acquainted with this, but this is probably one of the most unique capabilities of this model, because working in flexible mesh allows the model to resolve irregular geometry or irregular obstacles that you have typically in any area of application, urban area or even natural areas. Is that's what you have in nature. So the flexible mesh allows you to adapt to this environment, and it can do that because it solves all the equations in the triangle with any velocity distribution you have, and that's common to all the modules that we provide. The new some of the new MT module capabilities includes the following. We have the new module is a two-phase model. It's a two-phase in terms of the consideration of the water as a separate from the sediment. So we have sediment and water equations that not only assume that you have a single phase, but we consider the two-phase approximation in the space and time as well. One important thing that we added in the new module is that the gravity term now is not assumed to be quasi-horizontal as in the past, and in probably all the models that you can shop around, you will see that the approximation is assumes that you have horizontal flow. So even if you can apply almost any shallow water model in irregular surfaces where you have drops or variable gradients of the terrain, the approximation that the models use is that the gravity also occurs. The flow also occurs in the horizontal vertical plane. So normally these models do not project the flow in the actual slope, and that's one thing that we added because we noted that by capturing this in this approximation in this way, we get much better results than if we don't use that approximation. And that's I can provide some papers where this is demonstrated. The model considers spatially and temporally variable density, viscosity, and yield stress. You can have multiple inflows with variable fluid properties. You can have water coming from a tributary. You can have tailings coming from a different tributary, and they can all mix, as I will show you in today's application. You can simulate the mixing of these tributaries with initially static fluids. You can have a reservoir that is being affected by a landslide, and that the mix of the landslide material with the water will change the fluid properties and all that effects. You can consider rainfall over the material and how that rainfall affects the properties. And also you can have bed soil characteristics, particularly the concentrations of the different fractions can vary, can be different in the soil from that of the flowing material. You can have multiple sediment fractions. So the material is characterized, or you can characterize the material by having different size fractions, and each fraction can have its own volume concentration. The model can consider erosion and deposition. Now, this is not erosion of, just to clarify, because I've seen models that consider the erosion of the material that have already flown, or you get have moved already. We account for the erosion of the actual bed of the terrain or the river. So of course the material can also erode and can also move, but the bed can change in time because there is interaction of the bed with the flow. Okay, so in terms of the model equations, we have many more equations that we used to have in the original MD module that consider only constant properties. Now we have one mass conservation for the mixture of sediment and water. We have two momentum equations for the mixture. But then we have equations for the end fractions that may be available, the mass conservation equation for each size fraction. And then we have one equations for the bed erosion and deposition. So in total, we have, if you have, let's say, 10 fractions, you will have 14 equations to solve. And that's what the model solves for you. In addition to that, we have auxiliary formulas for deposition and entrainment flux and viscosity and yield stress variation, as I will show you. So in more detail, so we have a mass conservation equation for the mixture. And here we have the density and depth and velocity U and V, the components of the velocity. We have the momentum equations for in the X and Y direction. For the mixture, we have the mass conservation for each sediment fraction. So we have n fractions, we have n different equations. And then we have the bed erosion deposition equation that tells, based on the solution, how the bed is eroding or depositing, if that's the case. So this D and E terms here are the deposition and entrainment fluxes. And this deposition and entrainment fluxes are the ones that are used to represent how the bed is changing in time. So and there are other terms that I don't want to get too much into the technical details of this. In the manual, you will find all the descriptions of the different terms and variables. In addition, we have also, when you use the variable property option, that the viscosity and yield stress of course, the density, but particularly the viscosity and the yield stress can vary as a function of the concentration of the mixture, the volume concentration. So providing these expressions, the model can compute at each cell the viscosity and the yield stress as the flow is happening. Now, this is very important because in many applications, even though sometimes you can make the assumptions that the viscosity and yield stress remain constant through your simulation, there are many instances where that doesn't happen. And you have to account for that variation of yield stress and viscosity and density with the volume concentration. So if your volume concentration is changing, you can see here, this is experimental data. You can see how the variation of volume concentration in the usual range between 0.2 or 0.6 uh, uh, gives a very substantial changes in both in the yield stress and the viscosity. So what we have done is that we have used this correlation functions that allows the model to compute the yield stress and the viscosity based on a given data set of this that I'm showing here. In addition to that, we have the option provide the option to the user of using different rheological formulations, and these have been a common feature since the beginning of our of the module when we released a few years ago, because we thought that it's not every non-Newtonian fluids behaves in the same way, and there are many instances where the a tailings dam application, the material that you have in the deposit may behave better when you pick one specific formulation. And that's why we provided different options for that, and we still do that in the new variable properties model. To facilitate how you get those parameters, we provide a number of options in the model in which you can select from the literature the parameters that have already proven useful in other projects or other applications. And we do that for the viscosity and the yield stress. So by establishing a given concentration by volume here for the mixture, you can select one of the formulas that are used for viscosity or yield stress. But regardless of the value that you get there, if you use the variable viscosity and variable yield stress option, these constants will automatically translate to these frames here, so that the model dynamically computes the viscosity and the yield stress as it performs the computation. So one thing that is very important in the applications of tailing dams is how to establish the initial conditions. Now, in the QGIS environment, we establish the initial conditions. We have two different sets of the initial conditions. One is the raster initial conditions that you use for the actual surface or the elevations of the deposit that you have, you want to model. And then you have the initial concentrations of that deposit. So in the variable properties model, you need to give initial concentrations for each of the fractions if you don't want to have that as a constant. So you do that in the initial conditions layer, And in the initial conditions layer is very simple. The only thing you need to do, if you have an initial deposit as the one I'm showing here, you create a polygon that covers that deposit and assign an initial condition file. The initial concentration file that I'm calling here in the example initial CVS.txt file it only contains the initial concentration for each of the fractions that you are modeling in your application. So in this case, I'm assuming you have 3 fractions, and this will be the 3 fractions, the 3 concentration by volume fractions that will have initially this deposit. Okay. So that's an option. You don't need to provide that if you don't want, because if you don't provide these initial concentrations, the model will use the initial concentrations that you have defined for the rest of the area that I will show you in a minute. You also need to remember that to set the initial concentration from the raster, by the way, this is a raster that represents the deposit, the initial deposit of your tailings dam. Now, if you have to remember that when you're running the model in the data input program before hitting the run RiverFlow2D, you have to make sure that this option is selected, because this is the one that will ensure that the initial elevations of the deposit will be taken into account for starting moving the flow. Another important thing that you have to be aware of in this new module is that the boundary conditions are different, a little different. And this is because since we are using different fractions to represent the fluid, is no longer a constant property fluid now, you have to provide volume concentrations for each of the fractions that are coming into the mesh from the boundaries. So we do that in the boundary condition layer. In the usual way, we create our inflow polygons in the QGIS environment. The only difference is that now you have to have different volume concentration for each fraction. So as an example, if you remember the format for the data file, we have, it's a text file, we have the number of lines here, the first line, then we have time in hours, discharge, flow rate is the same thing, but now we have to have one column or one parameter for each time corresponding to the concentrations for each fraction. Now, this can vary for all the inflows that you have. And what I'll do in the example that I will show you, the applications for the Brumadinho disaster that occurred in Brazil a few years ago, the inflow that we have in the river will be water. And for that inflow, I will assume that all the concentrations are 0, because that's what characterizes the water. So it's clear water that is coming, that it will mix with the tailings. I will show you that in a few slides. Now, in reality, you don't need to worry too much about this when you're creating your spatial model, because when you go to the data input program, if you don't have the enough concentrations given, and when you touch in the open boundary condition panel, the model will tell you that you need to add more concentrations, and it will add that for you so you can fill up the concentrations here and save the data. So that's something that you can do after you have created your spatial model. Okay, so just before going to the details of how you apply, just a brief summary of what have been done to validate the model. There are many applications that have been published about the model, different algorithm formulations. Some of them are here. I can provide some of these references in more detail if you want. You can find your papers and read them. There, the validations include analytical solutions, but also comparisons with measured data and actual field data. There is a recent publication that is coming up that is that provides probably the most up-to-date verification of the model. That is by Sergio Martinez and Javier Murillo and Pilar Garcia. Called it a robust two-dimensional model for highly sediment-laden unsteady flows of variable density over movable beds. It's a Journal of Hydroinformatics and it's in print. So one of the recent verification that was done with the US GS large-scale experiment. We used a lot this to validate the model, and we talked about this in the previous webinar, so I'm not getting into a lot of detail here. I'm just showing just a brief example of what this entails. This is a field scale experiment with a high gradient. So it's all measured. There are many sensors all along, and you can hear the cameras making pictures, and also the type of fluid that was considered here. So this is the an animations of the actual simulation that we did in the model of the same experiment, and the colors indicate the density of the fluid, and these are the concentrations of the different fractions that were considered, and the model was able to replicate all the roll waves that occur with the different, you see here the variation of properties. And also the frontal wave location of different tests that were conducted was very well reproduced. So you can see that in the previous webinar. If you it's on YouTube, but if you want access to it, I just email me, and the email that I will provide at the end, and I will provide the link for the video. We did tests for the GPU. Now the GPU version, it's for the MT module is coming up next week. So what we have released so far is the CPU version. But you can imagine if we are solving that many equations, the CPU version, it cries for the GPU version to run faster. And as you can see here in the test we did with the Tesla K40, the speed up that we get for this particular USGS test is very, very high. It's 27 times faster. So the actual applications I want to show you how to set up today is based on the event that occurred in Brazil in a little more than a year ago, and most people call it the Brumadinho case, but it's actually that's the name of the town that is downstream. And the interesting part of this is that it was captured in video, and also we have data that allow us to verify the models and see how the model can replicate what actually occurred there. And one of the things that is important is to try to estimate this initial volume. That is it's a headache for many models, and what we decided to do here is not to make any estimation, just let the initial deposit be there, establish the initial deposit, and then let the model run with the properties of this deposit to estimate what percentage of the volume that was mobilized actually did move. And as you'll see, we get a very close replications of that volume. So the step-by-step process that we follow in QGIS environment with the model is very simple and it's very straightforward. We support the latest version of the QGIS GUI. By the way, the QGIS environment is software is free. It's an open source system where you do not have any limitations to install in any of your computers. Of course, RiverFlow2D model is not free. That's the way we have to continue development of all of these new capabilities. But one of the advantages of working with QGIS is that from the user point of view, you can install the model, the QGIS in any model, and even if you can run, if you have 2 licenses, you can run 2 simultaneous runs at the same time, but you can pre-process all of the data and also post-process all of the results without having to have a license of the model at all. You can also demonstrate or send your model results to your clients, and they can visualize the results even if they don't have any license of the model, only having QGIS, which is free for them. So that, I think, it's a very interesting option you have there by using QGIS. But the step-by-step process starts by adding the terrain data. This is the terrain data that we have for the Brumadinho case. You set a projection for that, and as you can see here, we have 2 data sets. We have a raster for the terrain, but we have another raster, which is this one here, for the deposit. And this will be the initial conditions for elevations in the deposit area. Then we add an initial condition layer, as I mentioned, the initial concentration layer in this RiverFlow2D. These are, by the way, the RiverFlow2D icons that give you access to the different functions that we have in the model. And then we set the initial conditions, as I mentioned before, within the deposit here. Then we set the domain outline. This is the limit of the area that we want to model. So the deposit is here, the flow will occur downstream. And I will point you out now that downstream here, we will see the Paraueba River. The Paraueba River is a flowing river that has a gauge here that indicated that the flow coming from the tailings actually blocked or obstaculized the flow of the river here, damped the river, and that is very obvious in the gauge that I will show you here. So we have here, we have here upstream from the river a boundary. Oh, okay, we selected the cells rise of 10 meters. Actually, there was a lot of in the actual simulation, a lot of refinement, but this was the general cell size that was selected here. The inflow from the Paraueba River included the discharge that was set to 500 cubic meter per second constant, and also, for this simple example, we use only a fraction, and the fraction has concentrations of 0. So we assume that we have clear water coming from the Paraueba River. Once we have the boundary conditions here, we have also an outflow boundary here that is a free boundary in this case. We generated the mesh using this tool here. We have a new way to generate the mesh. In the past, we only generated a mesh. We didn't include the cell elevations at this process only in the export phase. But now you can also generate the mesh and do the interpolation elevations at the same time. So this is the mesh with the colors indicating the cell elevations. This is a detail of the mesh on the surface of the deposit upstream. So when you have entered all the spatial data, then you export the result, the data files to RiverFlow2D format. And one thing you have to do in this particular case, that you have to set the initial elevations on the deposit, is to set this option panel here and click on this using initial water surface elevation raster layer and select the raster layer that represents your tailings deposit. So this will be your initial elevations in the tailings deposit. When you export the data, you get the data input program control data panel. And in the data panel, you have to select the mud and tailings flow, because this will be the module that we'll be using, and we need to add the data, the parameters that characterize the material in this panel. And then remember to check that you have the initial elevations read from the fed file. You also set the simulation time, the output interval. In this case, we have to use a very, very small output interval because the things occur so rapidly near the dam that if you don't use a very small output interval, you don't capture that in your outputs. Okay, so in terms of material data, we have divided the panel in two parts. The top correspond to the constant property model. So if you ignore or click out this variable properties checkbox here, you concentrate on the top. That's exactly what we had in the constant property model that we had before. So if you don't want to, you want to make an initial assessment, you want to, or if you are sure that your material is such that it doesn't change the concentration within space and time, you can use the constant property model as before. Okay, and it will run exactly the same module that you were running in the past. However, if you select the variable properties erosion deposition model, you will use all the capabilities of the new module, including the variable fractions. So you can add new fractions here, and this is dynamic. Let me show you briefly here in the actual panel here. So you can add fractions, you can add more fractions, you can add the data, the density of that fraction, the initial concentration, diameter, porosity, shield stress, friction angle. This is a factor that controls the transport capacity. If you can leave it 1, it doesn't have any effect. And the fraction that should add up to 1. So if you have 3 fractions, you have to make sure that, let's say if you use 0.3, then you have to use 0.4 here. So they have to add to 1 because these are the size fraction corresponding to each size, and size of correspond to each fraction can be obviously different, and you can remove the fractions as well. You can set the equilibrium concentration formula. You have 4 options here. We have found the wool one that gives very good results in experiments that we have conducted recently, and we added that as well. The setting velocity formula, we offer the same setting velocities that we had in the past for the suspended setting model. And we have here the parameters that we use for the variable viscosity or variable yield stress formulas. This term is something that we think is unique in mud and the BRIFlow models, because we include the pore pressure factor and the pore pressure term. And this was included because when we initially had the module, we started to do experiments with the data that we collected from the experiments and USGS particularly, and we had to include this term to be able to replicate that. So it is important to have that term in the equations as well. Okay, so when we have that, then we can run the model. Click here, run RiverFlow2D, and then run the model. And then when the model is running as usual, you get a visual representations of the water depth or the material depth. But you see here in the module that you have some in the information status panel that the model is actually read the variable composition of the material and so forth. And you will see here how the program proceeds in time. Okay, once the model finalizes, then you can access the results and create maps and graphics with that. And we have a new concentration and property versus time maps for the static maps. If you click here with this icon, then you select your mod file, and depending on how many fractions you have different options here. In this case, we have only one fraction. This is the concentrations of that fraction, the total mixture concentration, the density, viscosity, and yield stress. And you can select which output time you want, add it to here. You can select to have the cell maps where the cells are colored, or the raster map as well, where you have interpolation. This is an example of the cell map for the viscosity at a particular time. This is actually 18 minutes after the collapse of the dam. And you see here that the viscosity varies. And this is the flow coming from the river. And this is water. So you have very, very low viscosity in the water. This is the yield stress that is also variable. So you can plot all those static graphs and based on your results. So when you do that in the particular application, we came up with very good comparisons of the observed versus simulated. You can see here that the comparisons of what we got was very close to the area of inundation. Now, I want to point out briefly here that I've seen if you search internet, you will see applications of the Brumadinho dam that has been performed with hydrodynamic models with assuming water. So when you see the actual fluid that happened here, and you see a water model being applied, and sometimes they report that they came up with the same area as well, I start to question what the assumptions that were made to make that kind of applications, because when I see the results that we get and the results that other models get with water, it doesn't make any sense. And I will tell you why that doesn't make any sense. but we compare the areas in different locations. This is the Alberto Flores crossing. I will come again to this area to show you briefly what happened there. And you can see here, this is the final state of the flow. So if you have had water, you wouldn't see anything here because you don't have that deposit. This is a tailings deposit mixed with the erosion that this deposit caused in the bed, and that's what you get there. So you have to remove that. It doesn't happen with water ever. Now the estimated or observed depth at this location is between 4 or 5 meter, and we got 4.8 approximately on this average area. So we come very close to those values here. Now, if you in the QGIS environment, we can extract a cross section in the flow, and this is the crossing the Alberto Flores road here. And I want to show you what happens here with the, this is the initial cross section. So there is no flow. But as time moves, the tailings arrive, and the colors indicate the velocity. High is high velocity. This is very low velocity, the light colors here. But what you see here is that the fluid essentially stops eventually. So at some point, there is no flow at all. You see, the charge is 0. So it's not possible. And this is the remaining fluid that you saw in the picture before, and the accumulation also on that area. So, and this only happens with non-Newtonian fluids. It doesn't happen with Newtonian fluids of water. So if you see an application of a tailings dam with water model, I don't know what to think about that. Okay, so well, this is an animation. I already show you about this, but this is the actual the simulation that animation that we got here, and some of the observe versus simulation results here. The mobilized volume and the time of arrival to this location here near the dam was very close as well. Now, the final thing I want to talk about is the results at the confluence with the Paraueba River. You remember I show you that I told you that we have the Paraueba River downstream, and there is a gauge that is called the Alberto Flores gauge. It's about 5 miles from the dam. So what happened here was that the tailings came downstream and right to the river, dammed the river, and then the river at some point that was flowing with this level increased because it was dammed until eventually started to recede and was eroding that material that blocked the river at some point. So this is what actually happened and was captured by the gauge that existed at that location in the river. Now, what happens in the simulation? I want to show you, this is the initial concentrations, that is 0 in the river, Paraueba River. This is the tailings at some point in the, it's coming down the dam from the dam downstream, and you will see what happens when it reaches the river. So remember, dark is high volume concentrations, light means 0 concentrations. So you see, eventually the flow passes again, but let me go back and go back to the beginning so that you can see. Look at the how this area floods because of the damming that occurs in the tailings. So it increases, you see, floods this area here. Part of the sediment gets into the river, but eventually the river prevails and washes out all the material and goes downstream. So this is something that you can get in the model. I mean, it takes. I didn't measure the time it took for setting up the model, but it would take roughly about an hour to do the whole thing with this model, to do the whole application and setting up the model. Okay, this is a cross section, so you can see a little more detail of what's going on here. And you see here the initial cross section of the river, the Paraueba River. So it comes the damming effect, and then eventually goes down to its original discharge. Okay, now I wanted to show you to finalize a profile. This is a profile of the along the river and the confluence. So this is upstream, this is downstream. So this is the initial profile. It dams the flow, increases the whole elevations, and eventually the river starts eroding that area, and then it can pass through again. Okay, so that's what I wanted to show you. I think is you have seen the different steps that you need to perform this type of applications. And just a few closing remarks. The new model, we think, is a very accurate, robust, and fast model that can deal with tailing dam breaks, estimating the release volumes, or at least approximating the volumes. It's a much better way than having to estimate these volumes with different empirical parameters. You can study the interaction with the tailings of the streams, lakes, and reservoirs. And you can use the model for general hyperconcentrated fluid flows that include erosion and deposition. So you don't have to run a separate sediment transfer model or a water model separately. You can use that with the non-Newtonian approximation directly. Since we provide multiple rheological formulations and integration of the pore pressure, we have been able to replicate field scale experimental data that we think is more realistic way to represent the tailing dam breaks, run out, and mud and debris flows. The model GUI provides all the tools required to set up the applications I have shown, and there are many other tools that I didn't have time to show, but they are available in the QGIS environment. And the RiverFlow2D MT GPU variable properties model can run 24 times faster than the one core run, at least for the Brumadinho dam break study. Okay, so that's what I had. I want to thank you